you guys are going to have to do this at some point. So this is the graph of f prime, and from that, you want to sketch a possible graph of f from -4 to 4, but you also want to find out where the function, you want to answer all these questions. Where is the function of f increasing? On what intervals is the graph of f concave up? And where does it have local extrema? What are the possible x-coordinates? So they set you up with this little table, because these seem to be all the interesting points from -4. This is a closed interval, which means it starts and ends. And at certain points. So one intervals is, so from -4 to -2 is these, what is the sign of f prime? Positive or negative? Negative. No.
It's positive.
It's positive, okay?
That's the
So the derivative is positive. Graph if f prime is increasing. So the graph of f prime, the graph of f prime is decreasing. So this is the graph of f prime, which tells you that my function is going uphill, but it's concave down. Do you understand that?
Yeah.
Okay. So it's I'm kind of going to sketch little
like even though
pictures
f
of the
positive,
graph.
the original graph is
So it's the graph of the function is going uphill, but since the graph of the derivative is going downhill, that means that my function is going uphill but concave down until you get to that point. You understand? Because this is a graph of f prime. Okay? So let's look up here from -2 up until 0. What's the sign of f?
Positive.
Positive. Is it increasing or decreasing?
Increasing.
Increasing. So at that point, my function is concave up or concave down? It's increased. So the graph of the derivative is increasing. Concave up, because the graph of the derivative. So this, I'm going to sketching pictures of f, kind of little pieces of f. You know.
Yeah.
So there, it's concave up. Okay. From 0 to 1, the function is, my derivative is positive or negative? Positive. Is my derivative increasing or decreasing? Decreasing. Okay. So what does that mean about my graph?
concave down.
It's increasing, but it's concave down, just like this. Follow that? Okay. Is it A?
Closer to negative?
What? No, because it's going downhill from 0 to 1.
And like soon.
This is the derivative. Okay, so this says my slope is positive, but my slope is decreasing. Okay, so it's getting less and less positive until at this point my slope's going to be 0. Right? Okay. Okay. From 1 to 3, 1 to 3 on this interval. Girls. From 1 to 3, my derivative is negative or positive? Negative. And is it decreasing or increasing? Decreasing. It's getting more negative, right? It's going downhill. So it's decreasing, so it's negative and decreasing, which means it's concave down. See?
Yeah, I see this one.
Okay. And then from 3 until 4, it's still decreasing, but what happens?
It's decreasing less.
It's concave up. Okay. So we'll sketch a graph at the end. Okay. On what intervals is it concave up? We just answered that question. Okay. On which does it have local extrema? So look at the derivative. Who sees where I have local extrema? Where does the sign of the derivative change from positive to negative?
0.
This is.
No 1.
Where is the local extrema? So this is conceptually kind of. Just right here, I have a relative what? I have a relative maximum on my function. Okay. So between
Right.
at 1, I have a relative max. Because the slope changes from positive to negative.
How do you know it's relative?
How do I know? Because the slope is changing from positive to negative. Okay? So I got that. Points of inflection, anywhere the concavity changes. So I have a PI right here, right? I have a PI right here. I have a PI right here. 3 points of inflection. Follow? Where the concavity is changing from plus, minus, minus, plus. Yes, ma'am?
If the graph were to continue up, like out of 4 on the right,
Yeah.
no, the other side. But would that then be another like relative max?
Relative minimum, because it's changing from negative to
Oh,
positive.
okay.
Okay? Yes? Okay? We got that, and now let's sketch a possible graph. So I'm going to come over here to -4, and I know that it is, so from here, so let's put the little points on here. So from 4 to -2, it's doing something, and then from -2 to 0, it's doing something, and then from 0 to 1, and then 1 to 3, and then 3 to 4. Okay? And so from -4 until I get to 2 is kind of going uphill like this. Then I have a point of inflection going up like this, right? And when I get to 0 over here, I have another point of inflection and it starts decreasing. Right, point of inflection from here to here. Oh, it's still increasing, but I have a point of inflection. So this is a PI, so it's going from concave up to concave down. And then when I get up here to 1, right about here, I have a relative maximum and it starts heading downhill, right? And then when I get down here to 3, I have another point of inflection, but it's still downhill. And that would be a nice picture of the graph. Isn't that cool? Kind of cool. Yeah.
Is there anything that kind of looks like similar to that?
Yeah, it could be shifted up or down, but a lot of times what they'll say is at -4, the value of the function is 1, or at 3, the value of the function, they'll give you some points that it has to go through. Okay?
Have we gone over these particle problems we talked about?
No, that's what I was going to talk about next. Particle. You ready for particles? How about subatomic particles? Here's a particle. So with these particles, and I stole this out of the book because I didn't want to write all this stuff. What time do we get out? 5?
Yeah.
5.
I was just saying
Okay.
that.
So this is the motion of a particle along, describes the motion, oh, here it is. It says, this is, look at how innovative I am. I cut and paste these things out of the book, okay? So a particle is moving along the x-axis, and this is, why reinvent the wheel, right? So a particle is moving along the x-axis with the position function x of t is equal to this, okay? So it's moving back and forth. Find the velocity and the acceleration. So here is my x-axis. And let's just call this like, here's the wall, all right? And over time, the particle is just going back and forth, back and forth, back and forth, back and forth, like that, okay? So find the velocity and acceleration to describe the motion of the particle. So the velocity, you can just take the first derivative, okay? And then what they do, so here is a picture of the function if you were to graph it, okay? So what this says is it's over here somewhere, right here, it's over there, right? And then it's moving in front of the y-axis until I get to about here. And then right here, it starts moving backwards again, okay? Until I get to right here, negative velocity, and then it's got forwards velocity after that, okay? So that's what this particle is doing, going boom, 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 like that. And then it's taking off forever. So this, how do I know that? Well, by looking at the first derivative, which is velocity. So if I take the first derivative, which is this, and then I set that equal to 0, which I think I covered up, okay? I set that equal to 0, I get these 2 points. T equals 1 and t equals 11/3 if I factor that out. And then, so what that means is the sign of the velocity to the between 0 and 1, okay, is you're starting back here, but the velocity is positive, right? So it's moving from here, starts back here, and then it's moving towards the x-axis until I get to 1, okay? So it's going like this, and then when I get to 1, it starts moving to the left again. Because if I plug in a number between 1 and 11/3, I get at a negative number for the velocity, okay? And then after 11/3, the velocity turns negative. So after 11/3, time is 11/3. It starts not the displacement, just the time. It starts moving backwards. Okay? So this is a graph of the position of the function. This is a graph of the velocity of the function. What does this represent right here? What's the particle doing at these 2 points? Changing directions. Okay? These are direction changes. Direction changes. What would this represent right here? The minimum of my velocity function, where the velocity is getting negative, more negative, more negative, but then it starts getting less negative. What would that represent? That would be a point of inflection on the, notice too, this is a graph of the second derivative, right? Negative, the slope of the derivative is negative, slope of the derivative is positive. So this and this line up, those are a point of inflection on the graph. See that? Okay? These are direction changes. This is a PI right there, okay? Which also represents when the acceleration is changing from increasing to decreasing. So what they do is they take the second derivative, set that equal to 0, and they get, you get 7/3. I can't grab this. 7/3, and then to the left it's negative and to the right it's positive. So after 7/3, which is right about here, okay, the acceleration is negative, meaning it's not necessarily slowing down. This is where I got confused, because it's not really slowing down, because here the function is, it's not slowing down, but its velocity is getting more negative, right? So the speed is actually increasing up until this point. And then the speed starts decreasing, okay? You understand that?
Can you say that one more time?
So even though the velocity, the acceleration is negative, and the speed is increasing. Because if velocity and acceleration are going in the same direction, which we'll talk about later, then your speed is increasing.
But the speed gets less as you get closer to the bottom of that parabola, right?
The speed,
Like it's a small.
no, here the speed is, this is your maximum, well, maximum velocity would be up here,
Yeah.
right? But then this is, it's going pretty quick right here. But then the acceleration changes, right? So it's going, ooh, and then it's kind of, ooh, you know, it's still going backwards. So at that point, he's going like this. Ooh, at that point.
Yeah.
And then at that point, he's still going backwards, but less fast, you know. And then right at this point, he stops and he starts going forwards. It's
Yeah.
kind of confusing.
No, that's right.
Yes. Okay. So
What is this problem with asking questions?
I think, I don't know if I even put a homework problem on
You
there.
put one.
I did put one like this. So I just want to talk about this because I think it's worthwhile to talk about this. This is a real life problem in which girls. This is a real life problem. They put a bunch of points in there, and you could do a logistic regression, not a logarithmic regression, and you come up with this equation, okay? And then they ask you some questions, like use a calculator to approximate. So the hardest part is figuring out what window to put in here. I guess you could do a zoom fit or something like that, zoom stack. But So if it says use a calculator, reports that y20 to approximately 75, given the, what was the question? Find the logistic regression equation for the data. Use a regression equation to predict the Alaskan population in the 2020 census. So you would just plug in the year 2020 in there, except you would plug in 120 because it's years since 1900. And then it says, find the inflection point. So you could actually take the second derivative of this function with your calculator. It would be really hard to take this algebraically. Well, not that hard. But you could take the second derivative by plugging in this function into your calculator, okay? And then you take the numerical derivative of the numerical derivative. So it's ender y1 x1 which is the first derivative. And then if you do another xx after that, that will give you the second derivative equation, which looks like this. And this is a point of inflection, okay? And this is an important point, like when you're doing population growth models, because what would this represent if this were population?
Population, people over time.
Yeah, but what does the point of inflection represent?
When it's changing or
Kind of where if this is population, where your population is growing really fast, and then where your population kind of starts slowing down, right? It's still growing, but not growing as fast. So if we were here in Louisville, like if I were here in 1980 something, I would have seen this thing going up super fast, and you're going, oh gosh, Louisville's going to grow out of hand, it's going to get overpopulated. But then there's only so much room to grow, so it's still growing, right? People are still building around here, but not as fast, right? So that point might represent the point where the contractors go find other business or something like that, you know, or something like, or if you're a business person, that might represent the point where where you want to change your product to get something that's going to get more, the fast growth is stopped, and now you're at kind of slow growth or something.
When I define logistic regression, I just put the graph like way down. You didn't put it in.